Let's say I were to randomly pick 100 people and count how many of them had green eyes, and then I took that number, whatever it was, divided it by 100, and expressed that as a proportion. All right, now, central limit theorem says that if I was to do that over and over and over again, large number of times, so every time I pick 100 people at random, count how many of them have green eyes, calculate the proportion, and then graph up the proportion, graph up all those sample proportions. Central limit theorem says that all those sample proportions will take on a normal distribution. Here it is right here. Central limit theorem also says, down below here in this curve, central limit theorem says that the center of this distribution, in other words, the mean of all these sample proportions, will equal the true population proportion it is that I'm trying to figure out. So the mean of all these p-hats, these sample proportions, will equal the true population proportion. And central limit theorem also tells us that the shape of this distribution, in other words, its standard deviation, the standard deviation is given by the standard error. And we're using standard error because we're going to use a sample proportion in order to estimate it. Your notes say a few slides back that the standard error is equal to the square root of p hat times 1 minus p hat divided by n. Okay, we are going to be using the standard error when we go to calculate the confidence interval. Now, confidence intervals come with a level of confidence. So when you calculate them, you're calculating them at typically a 95% level of confidence, or as we'll see, we might only need to be 90% confident. Sometimes we want to be 99% confident, 99.9% confident, whatever. But the typical value is 95. Now, if we're going to use a 95% level of confidence, then we have to use the appropriate z-score that corresponds to that level of confidence. And the standard normal distribution tells us, if I go back up to this curve right here, that if I were to go out minus 1.96 over to positive 1.96 in normally distributed populations, that the area between those two z-scores will equal 0.95. All right, now where does that come from? Well, it turns out that if you go and you look up a z-score of negative 1.96 right here, and you look up the area to the left of it in your standard normal distribution tables, they will tell you that the area to the left, that's this little blue area over here, will be 0.025. Now, because the normal distribution is symmetric, if I've got an area of 0.025 to the left of a negative 1.96, I will also have an area of 0.025 to the right of a positive 1.96. And if I add these two areas together, 0.025 plus 0.025 gets me 0.05. How much area will there be in the center? There has to be 0.95 because the total area under this curve always has to equal 1. Okay, that's all great. We're going to use 1.96 every time we do a calculation involving a 95% level of confidence. But the central limit theorem talks about taking samples repeatedly, large numbers of times. But we don't do that. That's just not practical. We take one sample. So when I take my one sample and say this is it right here, I take a sample, I calculate that sample p-hat. Here it is right here. And I'm going to use that one value in order to give me an interval within which I expect to find the true population proportion. Okay, I take my sample, and for argument's sake, let's say my p-hat value falls right here where the red arrow is. And I make my calculation. I go out negative 1.96 times the standard error, and I go out plus 1.96 times the standard error. And I get this interval. There's my lower endpoint, whatever that number is going to be, and my upper endpoint. Question to myself is, does this interval contain the true population proportion? And the answer will be yes, because the true population proportion is right here at the center, and this number, whatever it is, falls between these two yellow fences. Okay, if I were to take another sample, say my p hat were to fall right here, and again I do my calculation. Does this interval contain the true population proportion? That is, this center value right here, and again the answer is yes, it does. If I come over here, does it contain the population proportion? Yes. Now, there are places, however, that it won't contain it. Let's say I pick my 100 people and count how many of them have green eyes, calculate my sample proportion, and the number falls right here. And I do my calculation, and here's my interval falling between these yellow fences. Does this interval contain my true population proportion? The answer this time is no. This center value does not fit between these two yellow fences. That's going to happen if my p hat falls anywhere from here, 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 up to about there. Now, on the other hand, if p hat were to fall in the upper regions here, I'm also going to have an interval that doesn't contain my true population proportion, and that's going to be true from here all the way over. Okay, now how likely is this to happen? Well, according to the normal distribution, 95% of the time I'm going to get a p hat, and when I do my interval, calculate my interval is going to contain my true population proportion. That's going to happen if my p hat falls anywhere from, I can't quite get on it, from the boundary between the light and the blue right here, right up to here. So 95% of the time, I'm going to end up with an interval that does contain the true population proportion. On the other hand, there's a 2.5% chance that it won't contain it, plus this 2.5% down here. So every time I take one sample and calculate the interval, there'll be a 95% chance that I'm going to get the right answer, but there's always going to be a 5% chance that I'm going to get the wrong answer.